Alright, and for the last video in section 15.5, we're going to look at problem 8, which is going to prove the two statements that we made at the end of the video on problem number 2, namely that the curl of the gradient of a function phi is equal to 0, the 0 vector there, and the divergence of the curl of a vector field, capital F, that's equal to 0, where here the 0 is a scalar. Okay, and we illustrated these two results with specific fields in question number 2. So let's go ahead and prove them now more generally. So for the curl of the gradient of phi, well, I've set up the determinant here for the curl calculation, and I've laid out the components of the gradient of phi on the bottom row. So we have the x derivative of phi, the y derivative of phi, and the z derivative of phi. So now to crank out that determinant, well, for the I component, I'm going to get the y derivative of the z derivative of phi minus the z derivative of the y derivative of phi. And then we'll get similar expressions for the j and the k components. Okay, and here notice that for the I component, I have the zy and the yz mixed partial derivatives, right? And we know that for a sufficiently nice, right, and this is why I mention here a sufficiently differentiable, so in other words, assuming that this thing is nice, and in particular it satisfies Clairaut's theorem, right, back in chapter 13, then these mixed partial derivatives are equal. So if I take their difference, I'm going to get 0. And the same is true for these other two components. And so the fact that the curl of the gradient of phi is the 0 vector is a consequence of these mixed partial derivatives being equal by Clairaut's theorem. All right, so that is it. Now, the problem goes on to say, conclude that if f is a conservative vector field, then its curl is 0. Well, that follows immediately, because if the vector field capital F is conservative, right, then by definition there's a potential function phi such that f is the gradient of phi. So if I take the curl of f, I'm really just taking the curl of the gradient of phi, which we just proved is equal to 0. Okay, now it does turn out that there is a converse, well, sort of a partial converse, I suppose, that if you know the curl is 0, does it follow that the vector field f is conservative? Well, under certain nice circumstances, and we're going to have to wait for Stokes' theorem in order to prove that. Okay, so let's now move on to part B. So this is looking at the divergence of the curl. Okay, so I've set up the beginning of the calculation at the top here. So here I've just written out the curl in component form. Okay, this is really just coming from the expansion of the 3 by 3 determinant that is used to define the curl. And then here I'm just taking the dot product of that with the del operator, right? Because I want to take the divergence of this thing. All right, so if I go ahead and just expand, right, I'm going to take the x derivative of the I component. So that's going to give me the xy derivative of r, and then the xz derivative of q. And then here, I'm going to take y derivative of the j component. So I'm going to get the yx derivative of r there, and the yz derivative of p there. And careful there with the signs, of course, right? Because we have that negative in front of the j component. And then for the k component, I'm taking z derivative. So I'll get the zx derivative of q and the zy derivative of p. All right, so now looking at this expression, notice I have the xy derivative of r here, and then I have minus the yx derivative of r there. And again, as long as things are sufficiently nice, those mixed partials are the same, so taking their difference, I'll get 0. And so here we're going to get all this cancellation happen, again by Clairaut's theorem, and that is the end of the proof. All right, cool. Well, that will do it for this section. I will see you next time. Thanks so much.